if we see where this map takes the line z equals 0, well, it goes x, y, 0. Yes, yeah, so x, y can mean, yeah, x, y, 0 goes to 0, 0, and then x, y. Yeah? But because we can scale 0, 0, a or 0, 0, b, it's the same point. It's just 0, 0, 1. Yeah, you can divide by it's the same point. And so maybe I'll draw a picture to illustrate. So it's quite symmetrical what happens here. We have these 3 points, which are drawn here, 3 lines that go through them, and then these 3 lines are mapped to the same points, okay? And you can work out exactly which ones go to which points. It's not hard exercise. Okay, so know this theorem. This is pretty much the big result for my project. And so what does know this theorem say? Okay, so I've been working over real numbers, which is actually a little bit more difficult. It might be more intuitive, but the result that was first proved was over complex numbers, which is harder to visualize, maybe complex plane, but imagine we just replace everything by complex numbers, okay? And it says basically that this complex Cremona, this should say group here. This is the group of all birational maps. So you take any birational map from the projective plane to the projective plane, the complex projective plane in this case, and it's generated by this map here, which we described, this Cremona involution, and projective linear transformations. They're just matrix multiplications which have inverses. So they're very simple maps, which we know in the usual setting. In projective language, it's just a slight difference, but it's the same really. And how do you go about proving this kind of? Well, for one, okay, know this theorem. A lot of people, when they hear this theorem, they think Noether. Well, the famous Emmy Noether is the very famous mathematician. But in fact, Max Noether was the man behind this result. This is actually Emmy Noether's father. A lot of people, he's not as well known, but in algebraic geometry he has a lot of influence. Very good mathematician. Okay, so how do we go about proving this theorem? Well, what the technique is going to be is we're going to take just any birational map. Let's say T. So we get RP. We use this symbol of a dotted line to, it's rational, it's not necessarily defined everywhere. So we take this map T, and then we're going to compose it with a series of, linear transformations and this map, this Cremona involution. And what we're going to hope is that the degree of our map drops. And then if we can do this for any birational map, then we can do it iteratively, and the degree is finite. So at some stage we go get to degree 1, and if it's of degree 1, then it is one of the projective linear transformations. So we have our desired result. One useful thing I'm actually going to talk about quickly is this Cremona involution. So this specifies these 3 points. But what we can do is we can compose this on both sides with a projective linear transformation, and we get what we call a general Cremona map. It's not going to be its own inverse necessarily, but we just take 3 general points, P1, P2, P3, and we're going to have the same map, but we're going to map the bad points of that to here, okay? And then we can compose it on the other sides to do something else, and this gives us what we call a general Cremona map. We'll see geometrically what this is doing in a bit, okay? Okay, so the blow up of the plane. So this is this interesting technique that we have, and for me when I first saw it, it was very bizarre, but we'll jump right in. And here we're going to be talking actually just about the plane that we're used to, the real plane. I'm going to stick with real numbers just because it's more intuitive. And here we go. We're going to define this surface, which I think of as living above our real plane. And so this is how it is. So the surface is living in RP, which is the real projective line. It's defined in exactly the same way as the real projective plane, but instead you start with R2 and you start with lines through the origin in R2. So it contains in it the real line. You can think of it as the real line plus a point at infinity. Okay, and this is the definition. You might not be able to see immediately what's going on, and don't worry, I have a picture in the next slide. Welcome. Okay. Okay, so basically, this is our surface that we're defining. Yeah, and this is going to be the blow up of the plane at a single point. Okay. And then what we're going to do, so we consider this surface living above it, and we talk about this canonical projection that goes down. And maybe algebraically, you can see it seems quite natural. We take the points here, and we just remove the alpha beta. We just stick with the x, y. You might ask whether this is well defined or whatever it is. It's actually well, hello. It's actually away from. Okay, so this map is defined going from S to R2. But we can talk about what happens in R2. Away from the point 0, 0. So if we talk about going back up, away from the point 0, 0, and in fact there's going to be a whole line which is mapped to the point 0, 0. Away from it, this map of this projection is bijective. So it tells us that actually away from this line and the point in R2, we actually have exactly the same surface. Yeah, it looks the same. Yeah, but we do have. But this middle line, which is mapped to the point 0, 0, we're going to call the exceptional divisor. Okay, and we'll often know they're just E. Okay, so here's what it looks like. Well, in fact, this is just a small part of what it looks like. And so it's a very nice picture. Enjoy. It took me a while to find it. And this here through the middle as well is talking about the exceptional divisor. Yeah. And you might be able to see actually geometrically that this projection coming down is with one-to-one correspondence with the bottom. You might not be able to see it, but if you look close enough, it does make sense. And actually, this exceptional divisor is like an axis. We project right down, it goes down to this point. Yeah. And so we can actually talk about the process of going back up, because away from 0, 0, everything's fine. We can go directly back up, and we go into the surface. We get to a unique point. One-to-one correspondence. But it's undefined at the point 0, 0. In fact, the map going back up is a birational map because it's rational. It's just undefined at the point 0, 0, and it's well defined everywhere coming down. So it's okay. We can work. We call this transformation from going up, blowing. We call this blowing up the plane. Yeah. And so it's going to be useful. What we're going to study is actually what happens to curves. What happens to curves in the plane when we blow up? So maybe I'm going to draw some pictures. So I mean, a very simplified picture that I'm going to draw is just of. So here we have the plane on the bottom and the point, and what we have here is this here we're going to call our exceptional divisor. Yeah, and one way we can look at this is that the lines that are passing through the origin here, we see them. They correspond to lines which are going across there. Yeah? And if you notice, they've all separated. So we have this nice picture here, which tells us something about what happens to lines which intersect. So if we have two lines which intersect in the plane, we take a point, we blow up at this point, and in our surface S, we're going to have our exceptional divisor, and we're always going to have these two separated. Yeah? Okay. So this is one thing. This is one nice thing that happens. But it also seems to do more than just separate straight lines. It seems to